Welcome everyone. It's a delight that we can go through this session today. It's going to be quite a fast session, going through sort of 45 minutes and having some questions. So I hope you find it intuitive. So a little bit about me, as Colin mentioned. I'm the product management leader in protection automation control products. That's within grid automation within GE. I do have a history in the railway industry, an enjoyable early career. You can see that I was at one time working as a distribution engineer on the West Coast Mainline Railway in the UK. And that was partly on new build projects and also for maintenance and refurbishment. Since then, I moved into what was Alstom at the time, now transitioned into GE, based in Stafford, UK, where I've held various roles for protection application engineering, business development, digital substation marketing, and more recently in my product management role, heading up a team here. Okay, so a few things that we're going to go through today. A little bit looking at different types of railway electrification infrastructure. A little bit on the type of feeding arrangements, which will dictate the protection schemes that we would need. Some of the components we'll go through, certainly concerning electrified catenaries, other feeding conductors. Then there's the plant itself, the feeding plant, such as transformer protection. A little bit on some conclusions and recommendations with some worked examples, and we'll save some time for Q&A. So let's make a start. First topic, rail electrification infrastructure. So first of all, you can see that there's roughly two different types of distributing the power to the trains. It's the trains that need to consume the power, they need to accelerate, they need to move from city to city or across the country, they need to move passengers, move freight, and so the right kind of traction power supply is important. So with it being a moving load, somehow that power has got to get to the train. On the left-hand side, we see one method of electrification, which is concerning overhead catenaries. So that's where we have live conductors in the air, and then we'll see later on there's a pantograph on the train which is making contact, and that's performing the task of current collection so that the train is powered as it moves along the track. So overhead wires is basically the overhead catenary form of electrification. On the right-hand side of the screen, you'll see something which is more an urban, a metro, potentially a regional type of electrification. You'll see there are no wires above the train, but actually marked in yellow here, these are actually shrouded live rails which are alongside the track. So usually in live rail electrification, of course, we have the two running rails that the train is running on, but then we'll have some contact which is made with, in this case, a safer shrouded version of a conductor rail. In some cases, it can be a third or a fourth live rail just exposed alongside, or in some cases in the center of the track. I've shown noticeably on the right-hand side that the live rail electrification tends to be DC. So usually we're talking something like 600 to 750 volts DC. On the left-hand side, you'll see actually that overhead catenaries are not always AC. Sometimes what we'll see is they can be something like 3 kV DC supplies, but getting more and more common really for certainly for high-speed routes, and also as the de facto standard, we see more and more 25 kV single-phase feeding to earth, and that's usually grid frequency, 50 or 60 hertz. But some AC overhead catenary supplies can be rated typically between 11 kV and 50 kV AC. Occasionally there'll be 15 kV at lower system frequencies like 16 and 2/3 hertz. But really the main focus of our webinar today is going to be on 50-60 hertz feeding for those overhead catenaries like we can see on the left. So to touch a little bit on the DC system, so interestingly, of course, we still need to distribute power to the trains, And usually what will tend to happen on metro and other DC electrified systems is the substations are relatively close together. They're just going to be every few miles down the track. And because the train here is supplied by DC, what it means is that there needs to be a long track, a trackside AC distribution system. And what I'm showing here is, if you like, the RA is the anode side of the rectifier transformer, and RC is the cathode side. So in the yellow dotted section, you'll see the live rail and the shoe. So the shoe is the point at which the train makes contact and collects the current from the live rail. And you can see that's down on a DC track feeder, and it's the job of the rectifier transformer and the rectifier to convert from the AC to the DC side. We'll see later on that the AC side protection is very similar to a conventional distribution utility form of feeding. I'm simplifying it here and showing a rectifier transformer with a certain number of pulses. You can see a delta and a star secondary winding, and then we've got a number of rectifier arms which are rectifying the supply to give us the DC that the railway needs. Okay, so moving on. Considering still that DC protection system, all I've done is I've just put two neighbouring substations. You can see there's two sets of rectifier transformers. Remember, those could be a few miles apart alongside the track. So we're having to connect each of those substations together with something like an 11 or a 33 kV distribution network along the track. So what kind of protection are we going to need? Well, of course, if we've got a distribution system, probably in this case they're going to be along track cable feeds. So anywhere we've got cables buried or in troughing alongside the track, it's a good opportunity to use line differential protection. So that's where I'm showing trackside cable protection. It's usually some kind of 87L function. So a standard protection relay line differential function. And here it's three-phase. It's phase A, phase B, phase C. So it's regular utility protection. The only thing that might change is the fact that it could be, as is in the picture here, the twisted pair of copper wires. It's not always a high communication capability, dark fiber or multiplex channel. But those two relays communicate with each other. They find a difference if there's a difference in current flowing in one end of the line compared to the other, which will then cause that section of the network to be tripped because there's an internal fault. So then if we move at effectively the intake, the anode side of the rectifier transformers, there's one little special there, and that's just because quite often these are silicon rectifiers, and the thermal mass of the rectifier arms is very low. So in other words, they heat very quickly. It's not an I²T heating effect. So all of the normal protection that you would have for that high voltage winding of the transformer would be pretty much regular, except there'll be a supplemented thermal protection characteristic. And that's what I'm showing at the bottom, where instead of an I²T type thermal function, we've implemented an I to the power 5.7 times T, which is reflecting of that very fast heating effect anytime you get overloads on the transformer. So what you can see here is that it might mean that, of course, the transformer rectifier unit can deliver 100% of rating continuously. It might be 150% of load for a couple of hours, but 300% of load only maybe for a minute. So the slope of that curve, noting it's actually a log characteristic, gives the kind of operating time of how much current is allowed to flow for how long before a trip will happen on the thermal protection characteristic. Okay, so as I mentioned, a lot of the protection on the AC side very similar to regular distribution protection, but with the supplementary curve that we get here for the advanced thermal protection. So moving more on to the focus of today, which is the AC catenary. Well, what are we looking at? I haven't picked the easiest picture to look at, because actually on the left-hand side with the train, actually a Taiwan example, what you actually see is this is an overlap in the wires. So this is where one tension length is coming into running above the train, and another tension length is ducking off out of the way in an overlap period. So if you can look at the yellow dots showing the marking, what do we have? Well, first of all, the train needs to make contact with the contact wire. And the whole idea of that wire is it's very straight, it's very level, it's true. Because of course the train, as it's moving at high speed along the track, it can't be trying to make contact with something that's not at a constant height. So typically that contact wire is about 5 meters in the air. And more often than not, it's copper for good conduction, and it might have an aluminium core for lightness. In turn, it's suspended from the catenary wire, and that's the top wire, normally on a cantilever arrangement. And the job of the catenary is just to suspend the contact wire level and true. Contact wire has some grooves down the side of it, and droppers which are hanging from the catenary are supporting the contact wire at a certain height. Then you'll actually see that there's an arm, a registration arm, and that's holding the contact wire in the right position above the track. So on straight track, it's just allowing that contact wire to slowly snake left and right across the top of the pantograph, so it's not wearing a groove. The pantograph that we're showing there is an arm. Usually it's got carbon tips, and we'll come onto that later. So usually if there's any wear, most of it happens on the pantograph, on the tips of the pantograph, whereas there will also be some wear on the contact wire itself. So the feed to the train, the live part is the catenary and the contact wire acting as a pair to distribute the power to the train. Train collects the power with the pantograph, collects the current, and it returns normally through some kind of a combination of the running rails. But because those running rails may not be the best conductor of AC current, then we'll see later that they're encouraged to return in a special aerial earth conductor, sometimes in a buried earth conductor, and you'll see sometimes there can be additional feeder wires which are supporting the network in maintaining the voltage. So let's go through in a little bit more detail some of those feeding arrangements. So what are we talking about as we look along the track? So in the blue box is effectively the in-feed from the grid. T1, T2 are the two supply transformers. What do we see here? A, B, C, D, E, F. That's really trying to show a two-track railway. So A, C and E are probably feeding north, and B, D and F is the track which is heading in for trains in the south direction. So we're taking the in-feed from the grid. We have two parallel in-feeds. They're not normally physically paralleled. Normally what will happen is T1 will feed all of the catenaries on the right-hand side. T2 would actually feed the catenaries which would be disappearing off the left-hand side of the slide. They then feed up to a midpoint, so the midpoint substation, by the two sets of catenaries in parallel, and normally that bus section circuit breaker would be open. Then on the right-hand side of that midpoint substation is exactly what we see on the screen, but as a mirror image. Because maybe 50 kilometers further down the track, if it was an urban type of arrangement, maybe even up to a couple of 100 kilometers away, if it was a high-speed network, you would have another grid supply point, which is feeding for, I guess you could say it was catenaries G, H, I, J, K, L, whatever is further to the right down the track. So if it was something like a high-speed line, then we're probably deriving that grid supply from 220, 400 kV transmission network, maybe the ratings of the transformers, 40 to 60 MVA. If it was an urban network, as I mentioned with the substations closer together, the in-feeds might only be 15 to 25 MVA rated, because we'll be deriving power maybe from the sub-transmission network, just at 110 or 132 kV. So why do we have this kind of topology? Well, first of all, we've got these nice reliable supplies from the grid, T1, T2. But of course, if T1 is out of service for maintenance, or if there's a fault on it and T1 is tripped out by the protection, then something still needs to supply power to catenaries A, B, C, D, E, F. And what happens there is that if there's any outage of T1, the bus section 1 will close, and the adjacent transformer will not only feed north, but it will feed south as well, so it feeds in both directions. So that's the first emergency feeding scenario. Second emergency feeding scenario is if something has taken T1 and T2 both out of the equation. And then what happens in that scenario is the grid supply point, which is somewhere over the right-hand side of the slide, hidden off the slide or behind the text. That would feed back and take over supply, and it would feed across to the left. Okay, so what we have to think is that's our feeding, that's the arrangement of what we have. And the one thing that I haven't mentioned is SS1, SS2, there are intermediate substations. You can see there's no infeeds at those points. They're just a point of paralleling of the catenaries. And that's quite useful because over many kilometres of track, we need to maintain the voltage profile at the pantographs of the trains. And the best way to do that is to lower the feeding impedance, so it's to allow as much current to flow in parallel as possible through the catenaries. So SS1, for example, it will be chosen as a point of paralleling between the tracks to encourage current to flow down both tracks, both sets of catenaries. But also it might be near a junction or a station or some other point of infrastructure where a line diverges. Because then, if there's a fault, say, for example, on the branch line, you don't end up affecting the main line. Okay, so in the game that we're talking about here, you know, say if it was something like a utility supply, you'd be talking about customer minutes lost as a KPI. We're talking more about train minutes delay as a KPI. So let's look at the type of feeding that we might have. So at that grid supply point, you can see that there's a supply transformer here. Now, in a lot of cases, that will be phase-to-phase connected on the grid. So what we'll see is that in an attempt to try and balance the traction load across a three-phase utility grid, probably one in-feed will be connected AB, so red-yellow. The next in-feed will be rotated and connected BC, then CA, then back to AB. So it kind of tries to distribute the traction load across the three phases. But of course, that will never be perfect. So sometimes we actually find that there will be a static converter, which is supplying the railway from the three-phase grid. For simplicity here, I'm just showing a phase-to-phase connected transformer at the supply, and then that's connected, you can see single phase in this case here. So the train is sat on the rails. The running rails are the point of exit from the train of the return current. So how is that current getting to the train? Well, we know the point of collection is the pantograph, so I've got the single arrow showing the current flowing onto the pantograph, but it's got to flow from the supply transformer through the overhead line equipment to get to that point. So yes, of course, it does flow through the catenary, or the combination of the catenary and the contact wire up to the train. But if we just suspended a wire in the air and left the current to do its own thing, what would happen is that return current would flow through the earth, through any parallel fences that happen to be there, any pipes that were buried in the ground, steelwork foundations of concrete buildings. So the current would just go from the wheels of the train back to the neutral of the supply transformer through any path it liked. So generally what will happen is there's a way of encouraging that current to flow back through a dedicated conductor. In this case, it's the return conductor. So the return conductor is nominally at ground potential, but what you can see here is there's a BT which is connected in certain overlaps in the wire. So the current from the supply transformer, the path of the traction current, actually goes through the bottom winding of the BT, the booster transformer, which is essentially a 1-to-1 ratio current transformer. So because the current has gone through the lower limb of that current transformer. When it wants to return back to the neutral of the supply point, it has to go through the top winding of the BT. So it encourages the current to flow through a known path, and it also puts the return current up in the air, very close to the current which was going out on the overhead line, and that helps to cancel out EMC interference on neighbouring communication circuits. The next slide shows a little bit more of a complicated method of feeding. The last slide we saw was just 25 kV on the catenary and nominally ground earth potential on the running rails. Now here what you see is something a bit more similar to we'll get on live rail, on high-speed networks. On high-speed networks, if we're not careful, we would have substations which are really cramped and close together. So the capital cost of that primary equipment would be huge. So we want to space those substations as far apart as we possibly can. So one of the ways of doing that is to use autotransformer feeding, which instead of being nominally a 25 kV supply, means it's a 25-0-25 kV. So it's it's a 50 kV network with a center tap. So it means that up in the air, above the train, you have the contact wire and the catenary, which are still at the regular 25 kV. But we also have an antiphase feeder. You can kind of think of it as being at minus 25 kV. So if we follow the current, start on the left with the two red chevrons, two red arrows you can see from the blue side of the supply transformer. So those two red arrows, they're flowing through the catenary. They're then moving along to the pantograph of the train. They're flowing back through the running rails. And actually, if the train was midway between autotransformers, AT, which are alongside the track, then half of the current would flow to the left and half of the current would flow to the right. So flowing left and right, one of those two red arrows that you see is that current which has been drawn directly from the supply. So then they go up to the center tap of the AT. So the blue dot between the green and the blue. That current itself, because it came from the supply, well, it's a circuit, so it has to go back to the supply. So what it means then is that current has to then go through the upper limb of the AT. So you can see one arrow of current is flowing up through the green part of the AT. And then that's then flowing back to the supply transformer. Now, because those autotransformers they're 25-0-25 kV, that one unit of current which has flown upwards on the upper limb means on the lower blue limb we're going to create an equal and opposite current. So we've got one red arrow pointing down. So that means that from both of the autotransformers there's actually a circulated current due to the autotransformer action, which is then hitting the pantograph of the train. So for each 2 units of current drawn from the supply, the train sees 4 units of current. So it's a way of effectively getting some of the efficiencies of a 50 kV system, but the train only sees 25. Okay, and it helps to boost the voltage profile of the catenary, even if the trains go quite distant down the track. In some cases, it can be single pole switching of switchgear. In some cases, it can be double pole, noting that we've now got 2 sets of energized conductors in the air, the catenary and the antiphase feeder. So let's look at some of the protection. And well, first of all, why do we need protection? So I mentioned that contact wire has to stay very level at a known location above the track to be nice and smooth for the pantograph as it passes. So the way of keeping that wire level is to very heavily tension it. So something like can be up to 20 kilonewtons. So that's 2 tons hanging off the end of the wire. Because essentially on most systems, what's keeping the tension is a set of bricks wrapped over a pulley system, which is just keeping those aerial conductors in tension. So we've got a very highly tensioned system. Also, we've got constrained electrical clearances. It's great if you've got a high-speed line because it's brand new, the fences are well maintained and solid, trees have been cut away, and any bridges which cross over the track have got lots of electrical clearance. They're high. If you think of some of the historical infrastructure, if you're trying to electrify a line which might be 50, 100 or even more years old, then instead of just getting a train through any bridges and tunnels, we've now got to get overhead wires above the track. So in some cases the clearances are so high you might have to drop the track, jack up a bridge deck, and even accept very low clearances to the point that sometimes the catenary wire even comes down to the level of the contact wire. The two pass through as catenary and two contact wires together, and then it swoops back up as we get clear of that low bridge. So as you can expect, those low clearances make the network relatively fault prone, especially on brownfield electrification sites. We want to limit the amount of current that's flowing because if we don't clear a fault, then that localized heating could cause the wires to become brittle with time. And the worst thing that could happen is a broken conductor, a dewirement, because what will happen then is the wire doesn't just necessarily fall, it tries to adopt the same shape that it had on the wiring drum. So it will snake out, it will whip out and potentially take out other tracks. So the very last thing that we want to happen, and we never want to happen, is for a wire to break and fall. And of course then, if we get that nightmare scenario and electrical wires do fall, then of course the section is dead, and then we have to wait for diesel trains to go and haul out any stranded traffic. So massive train minutes delay, massive disturbance. So this is all why we need to detect faults very selectively, trip out the right part of the network and protect it. Type of faults we can get, I've mentioned the low bridges. So we can get roosting birds sitting under bridge decks, especially large birds can cause a problem. There could be some loose material on board a train which is flapping and touching the catenary above it. Vandalism, it's not on utility systems, we don't have people above the overhead conductors, whereas of course when we have overbridges going over railways, and vandals can sometimes start throwing things over onto the debris onto the track, or even try to crack insulators. We can get dripping water in tunnels, we can get icicles, all these kind of things that could lead to faults. And what we'll find is that, especially on more of a brownfield site of electrification, then we could get one fault per mile of catenary per year on something like an urban network. So it is quite a fault-prone network, so we have to trip out. Usually what will happen is the debris has been blown clear, and then we can re-energize, and then we've stopped any further delay to trains. Trains carry on coasting, everybody's happy. Other things can be operational errors. If you've got a section of overhead line which is isolated and earthed for maintenance, if a train happens to overrun into that section, an electric train, it can bridge from a live section into an earthed section, which creates a short circuit. All of these things we have to take account of. So how do we protect? Well, with any kind of protection task, I guess we always start with economics. What's the cheapest way that we can protect this network? So typically for the sort of voltages we're talking about, 25 kV, if that were a distribution utility, a regular three-phase network, we would just look to use overcurrent. Now the difficulty with overhead catenaries is that when we take the railway network, sometimes or a lot of times the impedance of the supply transformer can be relatively high. You know, it can be something maybe like 5 ohms on a 25 kV network. So the close-up fault current for a suburban electrification, so right outside the door of the first substation, could be 6 kiloamps for a bolted short circuit. For a high-speed network, it might be 12 kiloamps. And this is generally because there's attempts made to minimize the negative sequence that would flow on the three-phase grid as a result. So the current is already relatively constrained, but then as we move along the track, so if that fault were 1 mile, 10 miles, 20 miles, 50 miles further down the track, then quite often it's something like 0.6 ohms per kilometre, 1 ohm per mile is the typical loop impedance of the catenary and the return earth circuit. Add into that the fact that we've deliberately put a lot of paralleling between the tracks to try and encourage the current to flow down multiple conductors in parallel. So that divides the current even further. So the current is low because of the supply impedance. It gets even lower because of the impedance of the catenary. Then we can have resistance involved in the fault because it could be vegetation that's causing is touching a wire. And then we've got that current further dividing down multiple tracks. So that's why we don't generally use overcurrent protection except for basic infeeds into depots and sidings, things like that. So really we need to use distance protection. Now distance protection, it allows us to mix current and voltage for the purposes of protection. So the impedance, we're showing the Z here, is voltage divided by current. And it's the vector division. So we take into account the phase angle of the voltage and the current. It's not just a scalar division. So what we can see at the bottom here is it could be that I've got my voltage at maybe 0 degrees. And in this case, the traction load, the current I, is lagging the voltage by an inductive power factor. So because that current is lagging the voltage, then that means when we do the impedance calculation, then we're going to get a leading impedance. So what might have been 20, 30 degrees lagging in terms of a current now becomes 20, 30 degrees leading, so above the 0 degrees line in that first quadrant that we'll see later. So good thing about having impedance is what will tend to happen if there's a fault on the network. Well, the current increases and the voltage will tend to decrease. So with that double effect in the division, what it means is essentially we're looking for an underimpedance scenario. And because we've got the phase angle relationship, we've got a good way of also using phase angle as a method of discrimination as well of what's going on. Looking at some of the characteristics, now we start looking at a distance relay. Well, why is it called a distance relay? Well, effectively, you heard me quoting so many ohms per kilometre or so many ohms per mile for the overhead line impedance. And that's just what we're looking for here. We want a relay which will protect up to a certain point distant from the relaying location. So that's why distance impedance are proportional to each other. So an underimpedance relay is essentially a kind of a distance kilometre calibrated device. So remember I said that a lagging current will create a leading impedance, and that puts it in the first quadrant on this polar plot. So R is the resistance that the relay is measuring, X is the reactance, and with the impedance being a combination of resistance and reactance. So what we can see is if there's a fault in the forward direction, so if there's a fault somewhere down the track in front of the relay, well, if that fault were right outside the door of the substation, the impedance would be 0. So that would be right at the intersection of the X and the R axis, right up close, actually in zone 1, distance protection zone 1. If that fault were further and further away from the substation down the track, then that fault would present more and more ohms of impedance. It would then be covered by zone 2, by zone 3, and I'll explain later why we have multiple zones of protection. So essentially, if I'm looking out into a catenary with a distance relay, I want to be able to protect all faults that happen down that catenary. So for whatever its length, wherever it falls along that dotted line, I need to be able to detect that fault. So easy. That fault could be resistive, it could be vegetation. So in other words, rather than just the basic short circuit impedance, which is on the dotted line, The actual impedance we would measure would be over to the right hand side somewhere. So it would be the catenary impedance plus some degree of R, some amount of R. So our detection characteristic must surround the dotted area, so it must be able to detect short circuits. It must be able to reach up to a certain point down the track. It also must be able to cover resistance. So that's why we start to create this four-sided characteristic as a need. Something which reaches to a certain point, which is the top line of the distance characteristic. Something which covers fault resistance, so that's the right-hand side of the characteristic. Something which is directional, because I've got relays which have got a specific job to look forwards. I've got other relays at different substations which are looking in the reverse direction. So I've got that bottom line of the characteristic in pink, and then also the left-hand line which is closing the zone. So quadrilateral is a pretty useful characteristic to have. Then when we look on the right, we've got to avoid the load. So the load, in this case here, we could say, well, let's have a look at the power factor. So if we've got something like a power factor of 0.8, that would mean that the load area would be up to about 37, 38 degrees leading the resistance axis. So whatever characteristics that we have got to avoid where the load might be, the heaviest load, plus also in this case you can see regen. So some trains have regenerative braking, so as they brake they act as generators and they put power back into the overhead line. That's normally with a capacitive power factor to avoid over voltages on the catenary, which is why you see typically that's in the fourth quadrant. On this sheet here we can see what we're trying to do. Now I've deliberately shown 4 tracks here, and the reason for that is 2 tracks is easy because actually the impedance of both conductors is the same. It's harder when we have 4 or more tracks in parallel because as I mentioned that the inner tracks might have 15% more impedance per kilometre than the outer tracks and might have a few degrees higher of characteristic angle. And the reason for that is because generally they're more inductive because there are more wires in the air around the B and C, whereas there aren't for A and D, for example. So we need to look down the track. We're generally looking on something like, the dotted line is something like on a 65 to 75 degree line angle, which is kind of the short circuit characteristic of the catenary. So what do we want to do? Well, if we've got a relay which is sitting on each track feeder, we've got to protect our track. So in this case, we're showing a relay which is protecting track A. So we need a characteristic which will protect as much of that as possible, but not overreach into tracks E, F, G, and H, or even overreach back around into tracks B, C, D, because they've got their own protection. So what we do is we set up a zone 1 which protects most of track A. We'll actually see 85% of track A. But then to complete the protection of track A, and then to start to provide backup, remote backup for faults on the other tracks, we actually then reach step a zone 2. So after a time delay, we allow a zone 2 to operate, and then with an even further reach, we have a zone 3. And the combination of those 3 zones will protect the track of interest, but they'll also start to provide backup protection if any downstream circuit breaker or any downstream relay fails to respond for whatever reason. So here's that shown as a philosophy. So normally, remember that zone 1 is protecting track A. We set that to 85% of the protected section, typically. And that's because we don't accurately know the impedance of that section. Remember that there's a contact wire which could have between 0 and 1/3 wear as the pantographs are moving. So over time, the impedance of the contact wire will change slightly. So we assume it's 17% worn, maybe on average. Then we could get uncertainty generally in the line impedance and the return circuit. We're also feeding the relays from a voltage transformer and current transformers, which are in themselves, they don't have perfect accuracy. And then the relay itself, because it's got to be so fast, typically sub-cycle, then it can't take a long time to get a highly accurate decimal point decision. So generally speaking, we'd be looking at 2% accuracy on distance zones, 5% in some cases, maybe 5% for CT-VT tolerance, 5% for line tolerance. So that's why we set to 85% so we don't overreach. Now when we start providing backup protection, then that can be when it gets interesting, because we say, okay, take the fault at F1. Now for that fault at F1, relay A, F1 is at 70% of track section H. The reason being is that remember that zone 1 on track section H is set to 85%. So with tolerance, the shortest point that zone 1 might actually be at is 70% of that track. So I never want my relay at A, B, C and D to overreach, because the relay closest to the fault needs to have a chance to see it first. And it's only after a time delay that I step out in that direction. So zone 2 needs to be set to the shortest of that fault at 70% of the shortest follow-on section, or 70% of the shortest hairpin section. And you can see the diagram of what we mean by hairpin at the bottom. It's where the current is flowing back down the track of interest. It's looping back around at the remote substation, and it's coming back round to the fault. So follow-on and hairpin calculations, you'll see, are really important. Not dwelling too much on the maths, this is what we actually do. So if we say that H is the shortest follow-on section, assume the fault is at 70% of H. And now what we've got to do is to consider how the current would divide, because we only consider a single point of failure. So why would we be backing up for a fault at F1? Well, single point of failure, it would mean basically that SS2 circuit breaker has opened correctly. So SS2, track feeder H, that circuit breaker is open. It means for whatever reason, H circuit breaker at SS1 has not opened. So we need to back up by tripping at A, B, C and D at the feeder station. So what do we do? If we take the follow-on example, we've put the fault at 70%. Now, up until that fault point, all of the fault current is flowing down four parallel tracks, A, B, C and D. So if you look at the overall feeding impedance, we've got 4 tracks in parallel. So the Z is the 4 tracks in parallel. Then the current has got to follow on past that SS1 busbar, down 70% of H. But then that's the overall feeding impedance. We've then got to take account of how that current divides between the tracks. Now, if it was a 2-track railway, it would be easy. You just multiply by 2 because we're dividing down the 2 tracks. In the 4-track railway, we've got this combination of A being the protected section impedance and R being the parallel combination of the rest of the tracks. So it will give a figure of approximately 4 because we're approximately splitting the current 4 ways, but it won't be exact. As I mentioned, there will be slightly more current will flow down the outer tracks than down the inner tracks. So for accuracy, we need to take that into account. And then, of course, we need to divide by 1.15 because we've already taken into account the potential for error at relay H. We've got to now take into account the potential for error at relay A. Okay, and then you get it's a similar idea for the hairpin arrangements. And whatever we calculate as the zone 2 calculation, it needs to be lower. It needs to be the lowest of the 2 results. Whereas for zone 3, it's a similar calculation, but you would need to put a fault right on the bus bars of the next follow-on section and all the way around back to the feeder station, because we've got to make sure we complete full backup protection as we go down the track. And that's when zone 3 kicks in after a time delay, as we see here. So we see what will tend to happen. So pink is where zone 1 for track A is protecting 85% of the track of interest. Then we get zone 2, which is reaching up to the next bus bar. It's going partly back round hairpin on tracks B, C and D, but it's also protecting follow-on tracks E, F, G and H. And then zone 3 in blue is protecting all the way 2 bus bars beyond, and also all the way back round to the feeder station, to make sure that we're not only providing protection for our catenary of interest, but also a follow-on one. And it's important to get this selectivity. So zone 1 is instantaneous, no deliberate time delay. So typically less than 20 milliseconds or sub-cycle protection to give fast response. That means that the relay itself is not time delayed. It hits the circuit breaker, and the circuit breaker, depending on its type, will take an amount of time to open. 60, 80, 100 milliseconds, whatever it might be. So zone 2 has to allow enough time for normal fault clearance to happen on the remote relays. So in other words, if I add the 60 plus the 20 plus another bit of a tolerance, there's a minimum time delay that I have to allow to grade between the devices, to time grade. And so that could be that zone 2 might have 150 to 250 milliseconds delay. Zone 3 could be 300, 500, 600 milliseconds. And what I didn't show on the other slide is quite often there's a reverse-looking zone 4, which is providing a little bit of local busbar protection if the fault is flowing in the opposite direction, which would have a long time delay normally of about 1 second. I'm not going to cover in detail what would happen on an autotransformer system, because the difficulty is that the autotransformers, they introduce a non-linearity. Remember, every time that you get currents which are flowing between tracks and they're paralleling, anytime you get autotransformer action, when you're transitioning between a 50 and a 25 kV system, that's when you start getting this hump effect as you measure impedances. So it means that any impedances you set for a distance relay can be accurate up to the location of the next autotransformer, but you have to take into account of the hump effect if you're trying to make them protect further. So it usually will need a system study, which doesn't need to be anything more complicated than an Excel sheet, but it's not just a simple hand calculation as is the case for a classical system. So some of the other protection elements that we will tend to have, so on the left are what will always be there. We've seen that the distance protection, ANSI 21, always 3 forward zones at least and 1 reverse. Because we've got voltage and current, we can have an accurate fault location. So usually to within 2 or 3% of the location, we can say how far down the track is the fault. So if you have to dispatch maintenance crews, you know where to send them to. Loss of volts, under voltage for things like interlocking will tend to be there. Instantaneous overcurrent is useful to have, because if you have a VT fuse blow and you've lost the voltage measurement for whatever reason, or an MCB is open, at least you can maintain protection for the network. You may want to have fast protection, dedicated protection as you close up a circuit breaker, because that's kind of a vulnerable time for the network. The chances are you're going to be closing a circuit breaker because maybe some maintenance work has finished. And maybe somebody has left a maintenance earth jumper attached. So switch on to fault and trip on reclose gives super fast protection to reverse trip a breaker as it's closed. Inrush detection, all those auto transformers down the track, where you've got trains also with onboard traction transformers. Second harmonic or other detection is important, because certainly some of the long distance zones like zone 2, zone 3 will probably need inrush blocking. In some cases even down to zone 1 may need some magnetizing inrush stabilization. Plenty of other functions like overcurrent, disturbance recording, any kind of programmable logic, interlocking, data for post-fault analysis. So whether that's waveforms like disturbance records or sequence of events are really useful. Then on the right-hand side are functions that we sometimes get. Load blinder, I'm going to go on to just afterwards. Also wrong phase coupling. But you can see that the devices that we will use, such as in the distance protection, these are all functions integrated inside to monitor safe operation of circuit breakers, breaker failures, to check synchronism. If we've got phase rotation across the network, so maybe phase AB one side of the bus bar, phase BC the other side as an in-feed, we need to check that we only close up if we've got supplies which are in phase. Auto reclosing, so when we have a fault, the chances are for most faults that the debris will blow clear, so it won't be persistent, so we can restore the supply to the catenaries after a time delay. We might want to signal between line end devices. Remember, I've said that there's that 15% at the end of each section, which is deliberately in zone 2 and is relying on a time delayed fault clearance. We can get the relays at opposite ends of the overhead line to talk to each other so that they each get instantaneous protection with no time delays. Sometimes defrost protection, so if you're the first train of the day on a very icy network, some rail operators, they put a deliberate loop short circuit or a resistor onto the catenary, which is just passing a deliberate current to warm the wire and melt the icicles. We have defrost differential to cover those scenarios. Okay, this just shows how load blinding can also work. So if we find we're wanting to set the zone characteristics, the quadrilateral, quite wide, but in certain cases the train load, in green, precludes us from being able to do that, then we can set a load blinder, which is stabilizing the protection, making sure that it doesn't operate where the load could be. But what happens is if the voltage falls below a setting, maybe 50% of nominal voltage, then we can override the blinder so the full zone characteristic is allowed to operate. So we get a really good benefit of load avoidance, so we avoid spurious trips on load, but we get the full expanded characteristic for sensitivity to faults. Wrong phase coupling, not used in many networks, but remember I said there could be the rotation across grid in feeds, AB, BC, CA, AB. So if somebody makes a switching error, then it could create effectively a cross-country fault between the two in feeds. And because the supplies are out of phase, it means that the impedance that we measure won't fall on the normal 65, 70, 75 degree line angle. So we need a specific characteristic, in this case that we can see set up off to the left, which is to cover those switching errors, those mistakes. They shouldn't happen. Interlocking is a much better way to do it. This is a just in case. I'm not planning to spend much time on transformer protection because generally the way we protect transformers is very similar to utilities. So at the in-feed, you can see that we might be taking off 2 phases of the supply, and then we've got a single phase output. In this case, I think we're showing an Autotransformer. So what we will tend to do is we'll have restricted earth fault protection on the high voltage side, 64 REF or transverse differential across the 2 phases, which is just doing a Kirchhoff's summation of what's the current coming in and what's the current going out on that particular phase pair. And then across the transformer itself, we'll have 87T, which is bias differential protecting both windings of the transformer. And then, of course, we can equally have the transverse differential on the low voltage side. And quite often we'll have some voltage protection. We'll have to detect magnetizing inrush. There'll be other current, voltage, and thermal type protection, potentially with RTDs looking for hotspots. And then the mechanical protection, the Buchholz or the sudden pressure gas alarms. I'm sure many of you are familiar with differential protection. So generally, whatever type of differential we're using, whether it's transverse diff, whether it's bias differential, then we're tending to take the bias current, which is effectively the amount of current which is flowing through the transformer. You can see here that this is not a vector here. This is just the algebraic quantity. What's the current flowing in? What's the current flowing out? So we divide it by 2 to see what's the through current. And then we look for the difference, the vector difference here. And what will happen is we'll get a fault in here if we have an internal fault in the transformer, so we'll cause the protection to operate. Whereas if there's an external fault or if there's load, we will stay in the restraint region and we won't operate. IS1 is the sensitivity setting of the protection. K1 will avoid if there does happen to be any tap changes on the network. K2 is a stability factor. so that we avoid operation for any CT saturation which might distort the currents. HS1 we take in is allowing us to, below here we would have magnetizing inrush detection before we're allowed to trip. When we're above the level which is magnetizing inrush, we don't have to wait for any inrush detection. So above HS1 we can have an instantaneous trip. And even HS2 is an unrestrained high set. So again, once we're sure that the fault is not on the opposite side of the transformer, we can drop in a very fast high set to get sub-cycle protection. I think all I'll say at this stage is Autotransformers, they have a very similar protection. You can see it's very similar to the low voltage side protection that we saw on the grid in-feed transformers. So it will tend to be restricted earth fault protection, and sometimes what we will get is we might have frame leakage protection, tank frame protection, which is kind of mass copper protection. So I'll move straight to the conclusions, recommendations. So thanks for sticking with me. So protection of AC catenary systems is a very challenging topic. It's not just a case of taking a three-phase utility relay and giving it a try on a railway network. It's a very dedicated topic. So why do I say that? Well, think of all the harmonics, the traction harmonics that are present. Some of the trains passing down the track, it's almost like that you're getting a sawtooth wave or a square wave instead of a regular sinusoidal current. There can be lots of harmonics. So that means that the relay itself has got to be very specially tuned so it doesn't react adversely to those harmonics on the network. It also needs to be very fast. So in the presence of all of those harmonics, in a load which changes very rapidly, which comes on, which comes off as trains accelerate, we need to make sure that we can get that form of protection which is very fast. Sub-cycle means that we're very unlikely to get a dewirement, a broken conductor. It also means that we've got a fast clearance of the fault on the network, which means that we stay within limits of something like 100 milliseconds for touch potentials for staff and the public who are waiting for faults to be cleared but happen to be alongside the railway line. So safety is paramount, speed and security are a way for us to do that. And by having that very reliable, dedicated product, then it allows us to maximize availability of supply, reducing train minute delays and making it a safer and much more reliable place to be. At the bottom of the screen, you can see that there is a short link, gegridsolutions.com/rail. That will take you to the home page for the P44T. So protection relay, P4 means distance, the middle 4 is the MICOM P40 series, T means it's a traction rail protection relay, P44T. Okay, and that's where we are today. I think I'll leave it there, and for those who can stay with us a few minutes, let's see if I can deal with a couple of questions. What kind of future do we see for electrified rail in North America? And what we see is the Department of Transportation, overall federal government, both in the US and also in Canada, are seriously looking at rail as a solution for the transport infrastructure struggles that we have. Of course, low carbon transport is a big factor in that. If we can move very quickly between cities without using aviation fuel, that's very useful. Because especially with those initiatives coupling greener generation from the associated utilities, such as wind and solar, it means that those trains are actually using green electrons as they're moving between the cities. And a few examples in California, Florida, Southwest, Las Vegas. There's probably 9 or 10 major rail projects coming on board in North America. Another question that we got is, why would we tend to use grid supply transformers, or could we use static supplies so power electronics to feed the rail network? And yes, that does happen. And what are the advantages of that? So remember I said before that if we have a single phase connected supply, we tend to pose a phase-to-phase load on the utility, which creates negative sequence current. So to avoid that unbalance, we can take a three-phase utility supply, 50-60 Hertz, and we can run it through a static frequency converter, power electronics, which will then generate the single-phase supply on the low-voltage side. It then also stops some of the harmonics passing through into the grid system as well. So it makes the supply to the traction network a lot more palatable to the utility than it would be otherwise. And it probably means that the utility doesn't need to reinforce the grid. Because if you're trying to get a traction in feed at a point where the grid doesn't have a large short circuit supply capability, then you're not going to be able to accommodate the level of negative sequence. So it really helps with the power quality to the grid. It also means that you don't necessarily need neutral sections and dead zones down the line. So if you have a conventional single-phase traction in feed from a transformer, we've said that the phase pair that we connect to will tend to rotate as we go longitudinally down the track. So that means we've got to have an isolated section, which is between those two out-of-phase supplies. So while the train crosses those, it has to power down, coast through, and then when it's clear of the neutral section, then it can power back up, connected to the new phase pair. Whereas if we have power electronics all the way down the track, then they can actually be paralleled because they're generating just the voltage, the current, and the frequency that's required. So that's my couple that I've seen quickly from the questions which are asked here. We've got a record of all the other questions that have come through today. As I say, we'll try and get back to you with good answers.
Thank you so much, Simon. Thank you, everyone, for attending. We look forward to seeing you again at our next Tech Talk. Until then, everyone, please stay healthy and look after yourselves. This concludes today's webinar. Have a wonderful day.